Hello and welcome to our webinar today. Today we will be discussing the use of Fronius string inverters in commercial systems. And we will do this with my colleague, Cyprian Okolo, is the technical sales advisor for the Western African region, based in Lagos, Nigeria. And myself, David Mwangi, I'm taking care of the Eastern African region. I'm based in Nairobi, Kenya. In our agenda today, we will talk about the Fronius inverters solutions. Then we go and look at the Snap inverters series. We give a special highlight to the Echo and the SIMO. Then we talk about project planning with Snap inverters. We will also discuss project planning with Tauro. Then Cyprian will go through the Tauro configurator, system analysis and maintenance, and give you some further information at the end. As usual, if you do have any questions during the course of the webinar, please feel free to post them in the questions area of the webinar control panel, and we will do our best to answer your questions as we go along. So let's look at the Fronius inverter solutions. And just to begin with, I'll give you a chronological order of the Fronius inverters from the start. So for those of you who have dealt with Fronius inverters, do know that we have quite some history making string inverters for grid-tied applications. And this started in 1995 with the Fronius Sunrise series. And these inverters are actually in use to date in some of the very early projects they were installed in. And if you look at this view, you can see that Fronius was making sort of a centralized design of inverters up to until the year 2013, after which the Snap inverters were introduced. So this is the period when a lot of rooftop installations started being done, and therefore installers preferred inverters that they could manage quite easily to maneuver with and to move to higher places. And therefore, Fronius started off with the Fronius Galvo in 2013. Then the SIMO, the Primo, and so forth have been added to the portfolio as we have gone along. We have other components or products that can be used to maximize self-consumption, such as the Fronius Home Pilot, which was introduced in the year 2017. And this specifically is for hot water generation using excess PV energy that your system is generating. Then we have also the Fronius Gen 24 Plus, which is a hybrid inverter. So before that, the only other hybrid inverter was the Fronius SIMO Hybrid, which was introduced in 2015. But this will be replaced eventually completely with the Gen 24 Plus. In addition to that, in 2021, we launched the Fronius Tauro, which is a higher power class for commercial systems. We will be giving a special mention of the Fronius Tauro today. And also in 2021, we introduced the Fronius Work Pilot, which is dedicated for EV application or for charging electric vehicles. So looking at the Fronius portfolio for commercial systems, we have 3 specific inverters that can be used for this purpose, starting with the Fronius Echo Snap inverter, which is available in the power classes 25 and 27 kilowatts with an MPPT voltage of about 580 to 850 volts. Then you have the Fronius SIMO available in the power classes 10 up to 20 kilowatts. The MPP voltage is about 200 to 800 volts DC. We do have also 2 Tauro variants. The first one is the Fronius Tauro Standard, which is 50 kilowatts. MPP voltage is 400 to 870 volts. Then you have the Fronius Tauro Echo, which is available in 2 power classes. One is 50 kilowatts and the other one is 100 kilowatts. The MPP voltage is 580 to 930 volts. So giving you some more specs on these inverters, of course, all these are 3-phase inverters. For the Fronius Echo, SIMO and Echo snap inverters, they have 2 MPPTs for the SIMO and 1 MPPT for the Fronius Echo. And then the Fronius Tauro Standard, which is a 50 kilowatt inverter, is equipped with 3 MPPTs, whereas the Fronius Tauro Echo for both power classes, that is 150 kilowatts, are equipped with 1 MPPT in each power class. So let's now have a look at the Fronius snap inverters for project use. So in this category, like I said, we have the Fronius SIMO available from 10 up to 20 kilowatts. So in between there, we do have 12.5, 15, 17.5, and then 20 kilowatts. So with the 2 MPPTs, you get quite a bit of flexibility because you can connect then maximum 6 strings directly to the PV inverter. And then because of the 2 MPPTs, you get the possibility for super flex design. So if you are looking at the differentiation between the Fronius Echo and the Fronius SIMO, then the biggest differentiator would be the number of MPPTs, because as you can see, with the Fronius Echo, snap inverter Echo, you have 1 MPPT to which you can connect also maximum 6 strings. But the Superflex design capability is a bit limited for the Fronius Echo. The Superflex basically means that if you have an installation with 2 orientations as far as the PV array is concerned, the Fronius SIMO would be able to, let's say, adapt better to these different orientations than the Fronius Echo. Although a lot of studies have shown that even an inverter with 1 MPPT with 2 different orientations of PV array, the loss in yield is not that significant. But of course, we want to maximize the yield, and therefore, whenever possible, it's better to use an inverter that can have the Superflex design capability. So just to give you also additional information that was not mentioned before, for the Fronius SIMO 10 to 20 kilowatts, the efficiency is 98.1, and then the protection class is IP66. And of course, all the Fronius static inverters currently are transformerless. The Echo version or the Echo variant has slightly higher efficiency at 98.3, but the protection class is still IP66. As you can see here, there's also a big differentiator between the 2 snap inverter versions, because with the SIMO series, we have an input voltage range from 200 volts to a maximum of 1000 volts. But with the Fronius Echo, we have a narrower input voltage whereby the inverter will only start feeding at about 580 volts DC. So the maximum also here is 1000 open circuit voltage. So when you're talking about commercial applications, we are basically talking about using of these inverters from systems that are starting from about maybe 50 kilowatts up to a maximum of a megawatt, or even slightly more, as you're going to see later. So, and this would be suitable for things like if you're designing systems for supermarkets, commercial buildings, company buildings, warehouses, farms, and so forth. And you can conveniently then combine the Fronius Echo 2527 and the Fronius SIMO 10 to 20 kilowatts. So that gives you a lot of flexibility because, like we said before, with the Superflex design capability, you can then integrate a lot of different orientations by mixing up the Fronius SIMO and the Fronius Echo in one setup. So therefore, if you do it with a direct connection, as we can see in this particular picture, then you do not need extra components such as DC combiner boxes. So therefore, you can get some savings there. And only one data manager will be required for every, let's say, a couple of inverters in the SolarNet ring communication loop. So those who have dealt with Fronius inverters do know that you do require a data manager for data communication to Fronius SolarWeb, as well as for things like export limitation or energy management within the Fronius inverter. So one data manager then would be required for every communication loop, or what we refer to as the Fronius SolarNet communication loop. So the Fronius snap inverters do offer a very simple installation process and as well as service. As you can see from this photo, we have the snapping concept. So it comes in two components. So the first one is the mounting bracket, and then you have the power stage unit of the inverter. So with the installation, once the mounting bracket is done, and of course, depending on the size of the inverter, then one or two people are basically enough to lift the inverter and snap it into the mounting bracket. And the most important thing to note is that once the mounting bracket or the inverter is put into the mounting bracket, there are two screws at the bottom here, one to the left and one to the right, that need to be tightened securely. So the applicable torque is also printed in the inside of the DATCOM cover. That ensures that you have proper marrying of the inverter to the connection area for DC and AC power. So that prevents damage that could occur due to sparking or overheating resulting from loose connections. So the mounting bracket itself is quite handy because this comes in anodized aluminum. It can be used for either wall or pillar mounting. No special tools are required. So depending on whether it's a wall or pillar mounting, then you would use the appropriate hole positions or a hole mounting kit accordingly. And then for the connection area, you have the integrated area for DC and AC connections, as well as the DC disconnect, which you can see here to the left. And for cabling, you can use both copper and aluminum cables for the Fronius snap inverters. So that also gives you a lot of flexibility in terms of the cable types to use. The direct connection of cables is up to 16 millimeters square, and within the connection area of the mounting bracket, there are no electronic parts. So it also has some protection against electric shock. So you will not get any safety hazards with using the mounting bracket. The cooling concept of the Fronius snap inverters is also something that needs to be understood in terms of when you're installing the inverters. As we know, all Fronius inverters are actively cooled, and this means they employ 2 to 3 temperature controlled fans, and therefore, depending on the type of inverter, air is coming from either the left or the right side or from both sides of the inverter, and then hot air is escaping from the top of the inverter through provided slots. So at the back, you have a heatsink that is cooling or is in contact with the electronics inside. So the cooling air never gets into the electronics component. So it's just basically flowing over the heatsink. And the heatsink is taking the heat away from the electronics inside the inverter. As far as mounting is concerned, for this to be efficiently done as far as cooling is concerned, we do require a minimum distance between inverters of at least 10 centimeters between inverters. So it's important also to take care of these considerations. So when you look at an actively cooled inverter, it gives you the benefit that the derating due to temperature is going to be at a much later stage, as we can see in this curve. So considering an inverter like a Simon 20 kilowatt inverter that has a capacity to deliver 20 kilowatt, and this being our ambient temperature on this scale, we can operate the inverter up to about 50 degrees ambient temperature when the input voltage of the DC side is about 600 volts before derating of power begins. So in the unfortunate event that the heatsink temperature goes from, let's say, between 75 to 80 degrees Celsius, then the inverter will start derating power output and will send you a state code 517 regarding a high heatsink temperature. If this temperature continues to rise and does not go down from this threshold, then at some point the inverter must stop to protect the electronics, and a state code 3 or 4 will then be sent to SolarWeb. But if you are on site, you can also see the various state codes if the inverter has a problem on the display of the snap inverter. We mentioned the Superflex design before, and the Superflex design for the SIMO inverters would allow you to connect, let's say, up to 3 strings per MPPT, and each string would have starting from 6 modules to a maximum of 24 modules. But of course, also this depends on the used modules, what is the maximum voltage of the module, as well as the AP currents. So the PV generator over dimensioning can be done to a maximum of 150% for the snap inverter SIMO, and this is what we refer to as the DC to AC ratio. Another cool feature about the Fronius snap inverters, doesn't matter whether it's the SIMO or the Echo snap inverter, is the integration by standard of the dynamic peak manager. So this is another algorithm on top of the normal maximum power point tracking that enables the inverter to continue giving you maximum yield, even in the case of partial shedding. So this therefore gives you higher flexibility and more yield in your system. And to give a better illustration of this, we can look at this curve where we have 3 instances in the production. So one curve is during midday where we have no shedding at all, and therefore we can reach a very good maximum power point, which we are referring to here as the global maximum power point. Then we have another curve, 9 in the morning with a bit of shedding. So with a bit of shedding, then it's possible that we have at least 2 maximum power points. One is what we refer to as the global maximum point, and then we have another one that would be the local maximum power point. So if you look at the position of the 2 maximum power points, the global maximum power point would be able to yield more energy for you than the local maximum power point. And therefore, what the dynamic peak manager is doing within the Fronius inverters is to check the best operating point as far as the maximum power point is concerned. And this is achieved by either increasing or decreasing the input voltage and working out the best position to deliver maximum power to the inverter. So when it comes to the options that are available for the Fronius snap inverters for commercial systems, we have the overvoltage protection, which can be ordered either as type 1 or type 1 plus 2 or type 2. And these are for the snap inverter Echo as well as the SIMO 10 to 20. And they can also be ordered for either single or multi MPPT. So on the first picture here, we can see the placement of the OVPs. And this, like I said, is something that you need to specify when you're ordering the snap inverter. So Fronius does give you the flexibility to say that if you have your own protection outside of the inverter, especially when you're using a DC combiner box, then you do not need to do double protection within the inverter. So you can save a bit of cost as well from the OVP selection. Then when it comes to the connection of DC power, if you have a DC combiner box within the setup, then within the Fronius inverter connection area for DC power, you would need a DC connector kit, and this can be used for both the Fronius SIMO 10 to 20 as well as the Echo 25 and 27 kilowatts. And this makes it possible for you then to connect bigger wire cables for plus and minus connection, starting from 25 millimeter square to a maximum of 35 millimeters square. And then when it comes to fusing, a lot can be done for protection also. If you are connecting your power, for example, directly from the strings to the Fronius Echo inverter, the Echo 25 and 27, you do require the fuses, and these are available, or the recommended one is actually 15 amps, 1000 volts. But if you, for instance, have a DC combiner box whereby the string protection is done within the combiner box, then you do not require the fuses within the Echo inverter, and you can just connect using the metal pins that are provided or supplied with the inverter as standard. So when it comes to the use of the Fronius snap inverters in commercial systems, let's look at the advantages, for instance, of the Echo inverter that you can get. So the number one thing that you will note with the Fronius snap inverter Echo is the high input voltage that we mentioned, 580 to a maximum of 850. That is at maximum power point. Of course, the open circuit voltage is limited to 1000 volts, and it has a higher grade of efficiency because the booster circuit within the inverter is missing, and therefore it means that for the steering voltage, you have to be quite careful when you are designing the steering voltage for the Fronius Snap Inverter Echo. If you do the connection directly to the inverter, it can save you on the DC combiner boxes that you would require. Overvoltage protection, as we said, is also optional, depending on if you are doing a connection using a DC combiner box. But if you do then connect the strings directly to the inverter, it's always recommended that at least you install type 2 OVPs within the inverter. But for better protection, you can integrate type 1 plus 2 OVPs. So the inverter itself is quite light, and therefore, if you look at the power to weight ratio, the Fronius Snap Inverter Echo is actually at the top of its power class. In terms of protection, we said it's IP66 number 4X. So this means that these inverters can also be used either indoor or outdoor. It doesn't matter. The only thing is that to note that this does not mean that the inverter can be operated in flooded areas. It means that it can withstand jets of water or rainwater, but never to be submerged in water, of course. When it comes to the Fronius SIMO, the advantages that you get is a broader DC input voltage starting from 200 volts to a maximum of 800 volts. The possibility of a lower input voltage is made possible because there is a booster circuit integrated on the DC side. Similar to the Snap Inverter Echo, you have the possibility to connect 6 strings, but in this case, separated between 2 MPPTs. So each MPPT is taking 3 strings. Overvoltage and fusing is similar to the Snap Inverter Echo. The weight is slightly higher at 43.4 kilograms, but in terms of the power to weight ratio, also the Snap Inverter SIMO does very well in terms of the figures there. And protection class is also IP66 number 4X. When it comes to the topologies of the systems that can be designed using the Fronius Snap Inverters, the SIMO and Echo, we have 2 possibilities. The option 1 that you can do is a centralized design, whereby the inverters are sort of placed next to each other. And in this case, you do require a DC combiner box, meaning that from the PV array to the inverter, DC power is traveling a longer distance than from the inverter to the AC control panel or the AC combiner box. In contrast, you can also achieve a decentralized topology whereby the PV power from the PV array, each string is then connected directly to the PV inverter. So depending on the SIMO, then you can connect 3 strings per MPPT, and then the Echo, you can connect all the 6 strings directly to the 1 MPPT. In this case, then AC power is traveling a much longer distance than DC power if you look at the connection, and therefore thicker AC cabling in this case is required for connection. So the advantage in the central topology is the fact that you can save a bit of cost on the AC cabling, but on the DC side for the central design, you can also minimize the power losses because the DC power is traveling quite a short distance. It's also possible to use the AC combiner box, as we can see here. So depending on how many inverters you have connected together. So if this, for instance, is a Fronius SolarNet ring, then all these 6 inverters would be connected to 1 AC combiner box, as we can see here. And then on the DC side, once you have the DC combiner box, like we mentioned before, you do require the DC connection kit or the DC connector kit within the inverter that is able to split this power to all the terminal connections for either DC or AC or DC plus or DC minus connection of the inverter, as we can see in this photo. With the Fronius Snap inverters, you can achieve very big installations. The first one we can see here is a big one that is In the Philippines, the total size is about 4.77 megawatt peak of PV power connected. And this system, of course, is using a mix of the Fronius snap inverters and the ECOs. And then also another big systems in the Ukraine, the size is about 51.9 megawatt peak. And also here we have a combination of light version snap inverter ECOs as well as full versions. So in this case, we have 65 full version snap inverter ECOs and 1,858 light version ECO inverters. So this system was commissioned in 2018. So you can see that you can achieve very big installations using the Fronius ECO inverters. But of course, it requires a bit of consideration when you're deciding to think about how you're going to interconnect all the inverters together. Because as we can see in this case, we have a few full version inverters and quite a number of light version inverters. Theoretically, as we know, we can connect up to 100 inverters per one data manager, but of course, that will vary from one design to the other, especially regarding the control speeds that you want for power production. So let's now go through the Fronius Tauro inverters and their use in commercial systems. So with the Fronius Tauro, we have two variations. We have the Fronius Tauro Eco D version or the direct version, and the Fronius Tauro Eco pre-combined version. So with the D version, this basically means that you can connect your string power directly to the inverter, and this is done by way of MC4 plugs that are provided on the DC connection area of the inverter. So if you have the 50 kilowatt version, you can connect up to 14 strings, and with a 100 kilowatt version, you can connect maximum 22 strings. So this makes it possible to do string monitoring at some point, and then the string fuses can be integrated as an option within the inverter. With a pre-combined version, it means that you would need then a DC combiner box, and within the inverter, you have V-clamps that are provided for connection of DC power. So for the 100 kilowatt version, we have 3 separation areas for DC power connection, and the maximum power cable connection in terms of size is up to 95 millimeter square. So just like we mentioned for the snap inverters, the differentiation between whether it's a central design or a decentralized design. So for a central design, we are talking about for the Tauro series, the P version, and for the decentralized design, we are talking about the D version. So with the D version, like we said, you connect the DC power from the arrays directly to the inverter. But for the central design, you do need a DC combiner box to be able to connect your DC power to the inverter. So in terms of the advantages of the two, if you're talking about a decentralized design, as we can see, we are going to require much shorter distances for DC cabling, but the AC cable is traveling a much longer distance. So in terms of the cost advantage for that, you do not require additional DC components such as DC combiner box, fusing as well as SPDs, but this of course is optional. The power advantage is the low DC losses, and then if you look at additional advantages that you can get with this kind of topology, you have a lot of flexibility. So the DC string fuses are inside the inverter. You have a reduced installation effort. So this means because you do not have to work on the DC combiner boxes, of course. And then in addition to that, you can do string monitoring when you have a centralized topology. So for the centralized topology, then you have the possibility to do, like we said, thicker cables on the DC side. But in terms of the cost advantage, the DC connector kit is not necessary, because like for the snap inverters, we say that when you use the centralized design, you do need the DC connector kit. But for the Tauro inverter, the V clamps are already integrated into the inverter. So therefore, the inverter costs are quite low if you look at the unit cost per watt. The power advantage here is that you have high DC voltage, and therefore this can also reduce the power losses of the DC side. In terms of the additional advantages, you have the connection, the possibility to connect 3 strings now instead of the 24 or 22 that we talked about for the 100 kilowatt. But this is provided using now 95 millimeter square cables. So there is easy installation because of the V clamps on the DC side, and longer cabling and gives you flexibility on where to place these inverters there, therefore is possible. So if you look at the 2 versions of the Tauro inverters, the pre-combined and the direct version, the backside or the DC area especially can be able to tell you which version you're working with. So for the pre-combined, you have the 9 or the 6 cable glands that are provided, that are integrated, but for AC power, you can connect up to 240 millimeters. For the decentralized design or the direct variant of it, we have MC4 plugs that are provided for connection. Then the string fuses, you have a choice of either 15 amps or 20 amps that are integrated within the inverter. For AC, we have still the same cross-section that is possible of up to 240 millimeter square. There is also the selection for the AC options of the Tauro inverter, because here you can also make your own kind of design on which kind of AC connection you want. So you can choose, for instance, to order an inverter that has the possibility to connect each phase on a single core. So we see here that we have been provided with 5 inputs or cable glands for AC power connection. And the cable size here can be from 15 millimeter square up to 28 millimeter square. The other possibility is a multi-core connection. So we have the connection here for AC power. So 1 input, and the diameter here can be from 16 millimeter square to a maximum of 61.4 millimeter square. And there is also 1 cable gland provided for earthing purposes. You can also order an AC daisy-chained version, meaning that this can also allow you to save on things like AC disconnectors for the inverters, because the inverter can be used to loop AC power from one inverter to the next, as we're going to see in the next session. And therefore, in this particular case, the cable size is limited to 11.0 to a maximum of 21 millimeter square for the cable glands that are provided here. So in terms of the cable glands or the V clamps that are integrated for AC area connection, this can be used to connect to a maximum of 240 millimeter square. I think we've already mentioned that. And it has a very unique design because you can actually flip it over, as you can see in these 2 illustrations. So when it's looking at this in the second illustration, that holds a smaller cross-section of cable. But if you open up this screw at the top, which requires an Allen key, as you can see also from this photo, you can flip over the V clamp, and this would allow you to hold a much thicker cable cross-section. So the cost advantage of having these V clamps integrated into the inverter, of course, like we said, no additional materials, cable lugs and stuff like that are required. It's compatible with both aluminum as well as copper cables. So therefore, you can choose on which cables are most cost-friendly to you. And then, of course, no special tools are required for connection. So just an Allen key is enough for you to be able to apply the right torque for that particular V clamp. So the power advantages, of course, they are low cable losses. And then additional advantage here is you have a lot of flexibility. The cable diameter can be freely chosen. As we have seen, you can flip the V clamp over for a smaller cross-section, and then for a bigger cross-section, you open it up and you can fit it quite easily. The other flexibility that is offered by the Fronius Tauro inverters for commercial systems would be the AC daisy chaining, and therefore This would allow you to connect up to 200 kilowatt of AC power in one block. So if you have, for instance, the 50 kilowatt Tauros, that means you can AC daisy chain 4 of them without the need for AC breakers in between. And then for the 100 kilowatt version, you can daisy chain 2 of those. So you have a lot of cable savings as a result. And like I said, no AC distributor is required, and with that 200 kilowatt power block, you require only one AC isolator. Active cooling is also employed in the Tauro inverters, and it offers even more benefits because it has a double wall design, and meaning that even when it's operating at 50 degrees ambient temperature, the electronics inside are at about 13.5 degrees less temperature because of this concept. So you can see where the cold air is being taken in from the inverter, and then it's being reticulated over the outer wall, and this is also helping a lot to keep the inverter components inside very cool. So the Tauro inverter also offers the unique advantage as far as service is concerned. So just like the snap inverters, you can swap a power stage if it becomes faulty. So we can see, for instance, if it's 100 kilowatt, we have 2 power stages. So we have each 50 kilowatt. But for a 50 kilowatt version, then we would have only 1 power stage. So if you have to send someone to site for a power stage replacement, only 1 person is enough, and therefore this has quite an effect on the OPEX of the system. So at this point, let me bring on my colleague Cyprian to continue with the rest of the presentation. Cyprian?
Yes, indeed. Thanks a lot, David, for your wonderful presentation. I will now be continuing from this point with system design with the Fronius Tauro configurator. And I want to believe that you can all hear me clearly and can also see my screen. So continuing, we're just going to basically show you how to make use of the Tauro configurator, which, as described here, is the right product in just a few steps. So basically, we're going to show you how to go from here, which is the landing page, to here, which is, of course, you arriving at a configured system. And to do this, like I earlier mentioned, is the use of the Fronius Tauro configurator, which is a free web-based or online tool that you can make use of, and can, of course, access it using this link. So in order to do so, you can just quickly just click on this link, and it's going to eventually take us to the landing page of the Fronius Tauro configurator, from where you can now do your configuration. For time constraints, it's basically going to be a brief demo, and then so that we can now continue with the rest of the presentation. So this is the landing page, and then of course, if you want to design a system, you can of course click on Start. So this will now take you to the first page of your configuration, where you're going to see 7 tabs. As you can see, system design, which is the page where we're on right now, inverter type, fuses, AFCI, SPD, AC connection, and AC disconnector. So just to take you through the function of these tabs. So for system design, you're basically going to select the kind of system you want to design, if it's a centralized system or a decentralized system, just like my colleague David has earlier explained in the previous slides. And then you'll next go to select your inverter type, the specific inverter you want to make use or deploy for this particular project, and then select your fuses if it's applicable, select your AFCI. The AFCI feature here is actually a new feature that was rolled in a couple of months ago. It's basically the arc fault circuit interruption feature. And then you can now select your SPD, which is a surge protection device, and then select your AC connection, select one from the different variations there are, and then select your AC disconnector if applicable. So we're just going to run through them so that you can see exactly what it means. If even up to now, you still don't know what the system type, or not particularly sure about the system you want to design, you can just click on this info button. It will just tell you all you need to know about the system. If it's a centralized system or a decentralized system. Basically gives you the explanation and the outlay of how these systems looks like respectively. So let's say we go for a centralized system. Next up is to select the inverter type. So you now select the inverter you want to make use of. So let's say we go for the Taro Echo 100. And then, yeah, so we can now see while trying to select fuses, it tells us that the Fronius Taro in the P variant does not require any built-in fuses inside the inverter. So this is basically because we're making use of DC combiner boxes. So in this case, the DC fuse protection must be implemented inside the DC combiner boxes. So next up is the AFCI, which in this case also is not possible because of the nature of the cabling, because you're coming with bigger diameter cables, so this would not be implemented for AFCI. Next up is the surge protection. So for surge protection device, you would now have to select between type 1+2 or type 2. Type 1+2 gives you protection against lightning current and overvoltage, okay? While type 2 gives you protection over just overvoltage alone. But then for regions where don't have a high frequency of lightning, it could be advised to go for type 2. Because this same type 2 provides smaller lightning current protection. But then for regions, tropical regions, for example, that has high rates or frequency of lightning, it is advised to go for type 1+2 protection, as it provides protection for both large and smaller lightning currents. So continuing, let's say we select type 1+2 protection. Next up is to make our choice of AC connection. If you decide to go for an AC daisy chaining, like David has earlier explained, you can click on this. But then note that once you click on it, you won't be able to have an AC disconnector integrated. This is because both the AC daisy chaining and the disconnector integration are both realized in the same chamber. So you either go for the other variations apart from the AC daisy chaining, so that you can now have that option. So just to put it in perspective, let's say we go for the single core version. Now you now have the option of AC disconnector, which you can decide to include or exclude, as you can see. So if we include it, it's now going to take us to the page where we'll have a summary of the system configuration. So we have a centralized system where we don't have a fuse required, neither do we have an AFCI required in this case. An SPD protection type of type 1, protection type 1+2 implemented. AC connection is a single core version with AC disconnector, and then you can now select the quantity you want to make use of, either 1 or 6 or whatever value you want to make use of. So with this, you've been able to achieve a centralized system. If you want to make additional configuration, all you need to do is to click on Add Configuration. It will take you to the Start page. So this time around, since we did the centralized, let's now go for a decentralized system. So let's select the same inverter in this case. This tool is free for you, so you can all try your hands on it and see what you come up with. So let's say in this case now, we can now see that we now have the option of selecting fuses. So you can go for either 20 amp fuse or the 30 amp fuse. And if you need more information, please click on the information icon to give you more details about the fuse rating to implement or to make use of. So in this case, we have the option of selecting arc fault, circuit interruption or not. So let's say we decide to go for the arc fault and then arc fault protection and then type 1+2 SPD. If we decide to go, in this case, with the AC-DC chaining, of course, we won't have any need for a disconnector, as earlier explained. There you have your yes, so there you have it explained that you cannot have the AC-DC chaining, you cannot have a disconnector when using the AC-DC chaining option. So when you click on next, it's now going to give you a summary this time around of your decentralized system configuration. And then if you're done, you can now click on next. If you click on next, it would now require you to provide further details for your project. So you can just decide to name it. I'm just going to name this one webinar. And then you provide your country information and location, total size of the system. And then most importantly, here also, you can add accessories. You can add your floor mount racks in case you want to mount the Tauro horizontally. Because for those who don't know, you can actually mount your Tauros horizontally and still will not have any ingress, because its ingress protection is very, very high. And then, of course, you have a safe system even as it is connected or installed horizontally. So this is how it looked like. So you would need these floor mount racks to be able to achieve this. So if you need it, you can now include it here. If you need protection hoses are basically to help strengthen the insulation between the cables in terms of temperature coefficients. And then you can also include DC disconnector locking devices to prevent unauthorized operation. And this is actually a normative order in some markets like Australia, for example. So after making your choices, you can now go ahead and export your configuration either as email, copy to clipboard, or can be exported as a CSV file. So just to tell you how this would look like, if you click on email, it will take you to your email page where you can now send your configuration to probably your procurement person or your Fronius contact, per se. And then you can now have your system design acknowledged and your system configuration put into play, per se. So there you have it. And then all you need to do is to include the particulars of the recipients, and that would be it. So this is basically for a demo. So that's basically how to design a system. If you want to start the work from the beginning, you could just click on start, and then you're right back at the starting page. So I believe that has done justice to basically how you can employ the use of the Fronius Tauro configurator. Let's now continue with the presentation, and with a reference in Costaria in Greece, where we have successfully implemented Tauro quite successfully. Here we have a 13 number Tauro combination of Eco 100s and 50s with a total cumulative capacity of 1.2 megawatt peak system. As you can see in this case, obviously, the AC-DC chaining has been implemented. In this case, as you can see, this is a decentralized system where you have your PVs directly connected to your inverter. And then at the AC output, you now have the AC output of this inverter linked to the that of this particular inverter, and then coming out and then going either to an AC distribution box or a point of interaction. So this is basically an overview of this same system. So let's now continue with the system analysis. Well, just to give you a perspective, ordinarily every investor or any client would want to have everything for free, but unfortunately that is not the case. There has to be a cost to a particular system. So now because of that, there now has to be a serious consideration about the total cost of a system. And then not just that, the profitability of this system. So this is actually put into perspective whenever a system is to be designed or analyzed in this case. So as earlier said, the total cost of a system is of course determined by the capital expenditure, which is also defined as the initial expenditure, and then the OPEX, that is the operational expenditure, which is defined as the day-to-day maintenance operations of a particular system or of an already installed system. This, of course, gives rise to the total costs of ownership of this particular system. So we're going to be taking a look at both the CapEx and the OPEX of the particular system. And we will be making reference and the comparison of products as this presentation goes on. So talking about CapEx analysis, to make the best decision on the best inverter to use, it is not only enough to consider the cost of the device alone. This decision has to be based on the comparison of all incurred costs plus the expected yields, just like I mentioned earlier, system costs, and then of course profitability of this particular system. So in order to give us a clear picture of this analysis, we're going to be making a CapEx analysis between Fronius Echo 27 and a 60 kilowatt competitor device. So this system is a roof-mounted system with a 400 kilowatts peak output and is situated in Central Europe. This is an outlay of how the system looks in the rooftop. The installed PV modules, like earlier seen in the previous slide, is 408 kilowatts peak with a total inverter output of 360 kVA. This, of course, amounts to 113.3 inverter ratio figure. So for the use of Echo 27, we're going to be needing 13
Hi, Cyprian. Please check your audio if you can hear me.
Is only a small portion of the total system, and then of course this big influence on the performance and ROI. We're going to see this subsequently. Next up is considering the BOS components at a much higher 33%. So in order to achieve or to see how the choice of inverter can have a big influence on the BOS cost, we are going to have a deeper look on the BOS cost to see how this is possible. So for BOS cost, going deeper into it, we can see that the grid connection, which involves the connection to the transformer, provision of the transformer, the switchgear connections, and the lights, all take up to 41% of the cost, followed by the 31%, which is scoped by the tracking system. 8% is taken by the cable tray and conduit, and then 20% is what is accounted for by the cabling, that is for the AC and DC. So yeah, so basically we have costs that are not related to the inverter or solar panels. These costs include the racking system, cable trays, and the main grid connection. And then you also now see that the inverter can have an effect on the cost, total cost of the AC/DC cabling, and then of course AC/DC distribution boxes, which you're going to find out eventually. So with the right system design, it is imperative to choose the right inverter so as to make huge savings. And in order to achieve this, we're going to make a model cost calculation between the same Echo 27 and the 60 kilowatt competitor for this particular example. We shall be looking at both centralized and decentralized systems. So going first with the centralized system, we can see for the Echo, Fronius Echo 27, that the BOS, DC BOS components, as you can see, and the BOS AC components all amount to about 7,753 euros. This was actually an analysis that was done, a real life analysis and not a simulated one. So these are actually the true figures. So we'll now take note of the components of this DC cost, which has to do with cabling from the module to the string combiners, and then from the string combiners to the inverters. So basically this forming the DC component, BOS DC component, and then from the inverter, we'll have to connect the inverter to the AC combiner boxes. So we have the cabling component here, and then of course from the AC combiner box to the transformer. So this cumulatively forming the AC BOS components. So combining these gives us a total of 7,753. So of course, strings collected in a string with the use of a combiner box, and for the Fronius case, only 2 DC cables are needed to complete the running to the inverter. And then DC cabling from the panels to the inverter, as you can see, in this case, this is 80 meters, are much longer than the cabling from the inverter to the AC distributor, as you can also see in this case. So next up is the 60, still on the centralized system, this time around for the 60 kilowatt competitor. In this case, only 6 string combiners are needed. Previously, in this for the Echo 27, 13 were needed. But then an important difference here is in the average distance. So in this case, it's 45 meters, but for this is 60 meters. And then on the cross-sectional area of the cable implemented. For the Fronius it was 35 mm squared, and then for, excuse me, for the 60 kilowatt competitor, it's 70 mm squared. So the cumulative components of the DC and AC BOS cost amounts to about 9,816 euros. So this just to inform us that the key difference in cost is actually due to the cable cross sections, and then the combiner and distribution boxes, as you can see, also affect the total cost. So the actual cost difference when compared between the two designs is 2,063 euros, which is in favor of the Fronius Echo. Great. Going forward, we're going to now look at the decentralized system, starting with the Fronius Echo. As you can see in this case, the AC run is much longer than the DC run. So the AC component would be higher than the DC BOS component. So, and most notably, as you can see in this case, there are no DC combiner boxes. So, but the summation gives us about 6,923 euros. So just restating what I've mentioned earlier, in decentralized designs, longer distances are covered by AC cables, and therefore big cable cross sections are required on the AC side, as noted here. For the 60 kilowatt competitor, you can see in this case that the expense is much more on the AC side, and then this would amount to about 10,327 euros. So the key cost drivers in this case are cross cable cross sections, and the AC combiner boxes. So other BOS components can actually come into play as a result of having significant effect on the cost. So these include the surge arresters, the AC fuses, and the AC and DC boxes, which all have their respective current handling capacities, for example. So the specific sizes would be allocated or would be apportioned to the respective components they are handling. So total difference in cost for the decentralized design is €3,404, also in favor of the Fronius Echo 27. So let's look at the summary, as you can see from this table. So in summary, there is a whopping 62% between the highest variation of the 60 kilowatt component or competitor and the lowest variation of the Fronius Echo 27 component. So yeah, so this means that it is much more valuable to and much more profitable to employ the Fronius option for both centralized and decentralized design, system design. So for the 408 kilowatt peak case example, there is a clear 62% cost benefit when using the Fronius Echo 27. Good. That was the CapEx analysis. Let's now have a quick look at the OpEx analysis. So for the OpEx analysis, like earlier mentioned or described, OpEx basically means the ongoing daily expenses for operation of a system. So this could consist of both planned and unplanned services. And majorly, the services or service activities could include module cleaning, cable connections or inspection, cable connection inspection, cleaning of the inverter cooling system, voltage and current parameter measurement and inspection, and of course, other activities related. So, giving us a Fronius advantage, would now like to make a comparison between an actively cooled Fronius Echo and a passively cooled competitor. So, we of course know that for actively cooled devices like the Fronius Echo, the rating is usually takes much longer time with a much higher temperature coefficient as against the shorter time it takes for the competitor to derate. And passively cooled inverter, of course, requires more cleaning in order to prevent yield losses from the accumulation of dust on the cooling pins. Also, the Fronius PC board replacement concept allows only one personnel to carry out service operations, as against the case where we would need larger, more engagement, like crane arrangement, and then making arrangement for much more manpower to carry out services for larger commercial inverters. So let's now continue to give us a Fronius advantage with this OpEx table. This OpEx table, of course, gives us the real analysis of the OpEx analysis of the passively cooled device and the actively cooled Fronius Echo 27. So as you can see from this case, in terms of site visits per year, scheduled maintenance is actually done biannually, while service callouts can actually be done once in 2 years. And then you can see that there's a stark difference when with the use of the Fronius Echo 27 that is actively cooled. Scheduled maintenance is once as against twice using the passively cooled device. And then of high note also is in terms of scheduled maintenance, in terms of total duration in hour. As you can see, that of service callouts is quite less. In fact, less than half of that of the passively cooled device. So at the end of the day, once all the costs are accumulated, we have an accumulated cost of 1,800 euros for the passively cooled device, while I have an accumulated cost of 720 euros for the actively cooled Fronius Echo device, thereby having a slightly above 1,000 euro annual savings per year when making use of Fronius Echo 27 in this example. So, having done both analysis, let's now look at energy yield, because CapEx and OpEx comparison are really not enough to determine the cost effectiveness of the choice of inverter to be made. We should also have a look at the expected energy yield, which should also form a good decision-making perspective, because expected and annual energy yield, of course, used to determine the ROI, which is the return on investment, and the levelized cost of electricity. The levelized cost of electricity is given by the summation of the OpEx divided by the energy yield kilowatt hour over a given period of time. So this gives us the levelized costs of electricity in euro cents per kilowatt hour. Now, to put this in perspective, the same comparison was done between the actively cooled Fronius Echo 27 and the passively cooled 33 kilowatts competitor. And you'd want to find out the effect on yield due to the derating behavior, as earlier explained. So the energy yield analysis here was done using the PV-SYST simulation, and specific energy yields for the two inverters are shown in the table, as you can see below. All taking into cognizance of the inverter temperature between the ranges of 10 to 45 degrees Celsius. So the results obtained are a total of 1,273 kilowatt hour per kilowatt peak for the Echo 27, while that of the 33 kilowatt passively cooled device is 1,222 kilowatt hour per kilowatt peak, thus giving us a 4.17 yield difference between the Echo 27 and the 33 kilowatt passively cooled device. So for a final analysis, considering actual earnings and savings based on the following data, you would want to have an extrapolated look at the situation over a 15-year period. So when this was done, the annual yield for Echo 27 is given at, of course, according to PV-SYST, is given at 519 megawatt hour, while that of the 33 kilowatt competitor is given at 497.3 megawatt hour, all with a feed-in tariff of 7.9 euro cents per kilowatt hour. So, giving us the Fronius advantage, as you can see from this graph, which was plotted from the figures obtained from this analysis, we can see that there is a 41,000 euro difference between the Fronius and the competitor product, which of course puts Fronius at a very, very good advantage for this particular system, analyzed over a 15-year period. Great. So that basically brings us to the end of this presentation for today. So I'm just going to give us further information on where you can easily get information as an installer. So all you need to do is to go to our website, which is www.fronius.com. Please select the Solar Energy Business Unit. And then for installers and partners, you can now select that. This would, of course, bring you to the Home tab for installers and partners, where you can have access to information about products and solutions, technical data, info center, service and support, downloads, and contact. Good. So recordings are also available on our homepage, where you can get operating and installation instructions. You can also get how to and installation videos, and then of course webinar recordings, especially that of our Sub-Saharan Africa playlist. Here we have a compendium of all the webinars that we have presented so far, and including this one. You can find it using this particular link. If you want to have access to our Fronius solar energy team, please access them via this respective information as displayed on this slide. If you want to have access to us directly, that is the technical sales advisors, please do so according to the technical sales advisor for your particular region. Myself, Cyprian Okolo for the Western Africa region, Byron Kotzer for the Southern Africa region, and David Mwangi for the Eastern Africa region. Great. So that brings us to the end of today's presentation. I want to thank you all for finding time to attend this webinar. We hope you got all the information you were looking for or looking out for. And until we come your way next time, we want to say a very big thank you once again for attending, and goodbye.